More often than not, we will give you the names of the formulas, and then you need to be able to write the formulas from the names that are given to you. So if I have potassium iodide, this is K that has a +1 charge, iodine has a -1 charge, so when you crisscross them, it's just Ki. I'm getting their charges from the periodic table. A lot of these you should maybe have memorized just because you've used them enough, but of course you will always have a periodic table available to you. Plus sodium nitrate. Sodium is Na that has a +1 charge, and nitrate is NO3 that has a -1 charge, so when you crisscross them, it just becomes NaNO3. So when I put them together, they're going to, the outside ones go together, the inside ones go together. They switch partners. So I end up with a combination of KNO3, potassium nitrate, plus what? NaI, sodium iodide. What? This is already balanced. We did skip balancing on this one, but that's fine. Just in the interest of time. What was the one number? Cool. In front of HCl, so 2 hydrogens, 2 chlorines. Over here I have 2 chlorines, 2 hydrogens. Everything else is 1. Balanced. Like we saw in this one, it's usually pretty easy to balance these things. This one is already balanced. There were no extra subscripts because everyone's oxidation number was 1, so then when they reformed new products, that's what you had. Then we look at, is this an acid-base reaction? I don't have any acids, I did not produce water, not looking at acid-base. Then I decide, is this going to be a precipitate reaction? That's my only other option, so I have to figure out what's my precipitate. So KNO3 is bonded to nitrate. Nitrate is soluble, and there are no exceptions. So I know that this is going to be aqueous, AQ. And then NaI, sodium iodide, I is right here. It is soluble unless it's bonded to one of these exceptions. Is it bonded to one of those exceptions? No. So is this soluble or insoluble? Soluble, which means that I would write what next to it? AQ. So what's happening in this case is I have potassium iodide. This doesn't tell you the state, but I'm telling you it's aqueous, and this one is also aqueous. We could verify that by looking them up on our charts. So what happens in this case is you have potassium ions, iodine ions, sodium ions, and nitrate ions just floating around. They bump into one another, they'll form their new compounds, but then nothing really happens. If it stays in an ionic, or if it stays in an aqueous solution, you're just going to have these free-floating ions, maybe as your reactants, maybe as your products, but there's no telling because they're all going to be separated. So this kind of goes back to Max's question from earlier of, would you be left with any of these things, any of your reactants still? And the answer is yes. The way that we would get this back, so like if we were to force this to form actual compounds, we would have to evaporate off that water, and what you would be left with is some of this, some of this, some of this, and some of that. So you would have all of this left. When this happens, though, if you have all aqueous solutions, again, it just sits like that, so there's nothing that's actually happening. When you observe this, you're not going to be able to tell that it's dissolved. You'll just be able to tell that you didn't form a precipitate. So this is when we say that no reaction actually occurred. If the reaction is not an acid-base reaction and both of the products are soluble, meaning that they are both aqueous, then no reaction has occurred. So that's why if it is a precipitate reaction, you have to check both of them and see if you actually did form a precipitate. So this one I would say no reaction. Although if it was one, it would be closest to precipitate. But we can't call it a precipitate reaction because no precipitate actually formed. No, a salt is any ionic compound. Salt just means it's ionic. So if I have cation, anion, it's considered a salt. Every single salt is cation, anion. Then we have calcium hydroxide reacts with hydrochloric acid. Calcium hydroxide is CaOH2 plus HCl. Calcium will go with chlorine, hydrogen will go with hydroxide. The outside ones go together, the inside ones go together. So calcium chloride is my new product, CaCl2, plus hydrogen and hydroxide, so HOH. I was just doing all the crisscrossing in my head. Calcium has a +2 charge, hydroxide has a -1, this is +1, -1. So when you re-crisscross them to form your new products, you're using the charge of everything with its partner. So this is water. So we formed water, which means we should already be on high alert to what type of reaction? Acid-base. This is the first time we've formed water in one of our compounds. So recognize HOH as water. And this is part of why we learned that shortcut of breaking water into hydrogen and hydroxide when you're balancing, because that makes it so much easier to balance it. So I have Ca, OH, H, and Cl. So if you think of them as 4 separate things, I have 1 calcium, 2 hydroxides, 1 hydrogen, 1 chlorine. On my product side, I have 1 calcium, I have 1 hydroxide, 1 hydrogen, and 2 chlorines. So where can some coefficients help me? Two in front of HOH, 2 times 1 gives me 2, 2 times 1 gives me 2, 2 times 1 gives me 2, and 2 times 1 gives me 2. So the 1s are balanced, 2, 2, 2, 2. Good. No. So if you have an acid-base reaction, then no precipitate would have been formed, so they should also be aqueous. Water obviously is going to be aqueous. Water is, but if you look this up, this tends to confuse students, so I like to point this one out, and that's why I also make a big deal that hydrogen is not an alkali metal cation. I know it's above the alkali metal group, but you know that hydrogen is a non-metal, so if you look up OH on your periodic table, it says insoluble except for when it's bonded to one of these. I've had plenty of students tell me that HOH is insoluble and forms a precipitate. That is water, you guys. So recognize it as water. This is going to be aqueous. It is aqua. Like, that is as aqueous as it gets. Generally, I'm not super strict on that. Because like I said, I would usually ask you to tell me what your precipitate is in a separate way. So I would say, like, circle your precipitate, or I would say write your precipitate on this line. I also want to point out that if that is the case, if I say write the precipitate on this line, the full compound is your precipitate. So just your sulfur anion is not a precipitate. Hydrogen bonded to sulfur would be your precipitate. Does that make sense? Same thing with up here. So what I'm saying is the thing that's listed is the anion, but what is actually your solid that's formed is a combination of both. So you would list the full compound. Do you want me to do the last one with us? Really easy. Alright, HCl and NaOH. Did you have a question, Cannon?
Yeah. For the potassium iodide one, you would still be like a double replacement, right? Because you didn't write it out right?
This one, I guess I would say double replacement, sure. But I would still say no reaction. So don't call it a precipitate reaction unless there is an actual precipitate. You can't tell, so in this one, you can't tell that there's no reaction unless you actually go and find the products, versus in a single replacement reaction, you could tell that the reaction wasn't going to occur before you made any product. You could tell, is this one going to actually replace the other? So hydrogen and hydroxide get together here, and then sodium and chlorine, so NaCl. And it's already balanced because everyone has an oxidation number of either +1 or -1, so there are no extra subscripts. This one, is it acid-base or... I made water, I started with an acid, this would be acid-base. It still falls under the double replacement umbrella, and same thing with this one as well. I started with an acid, I formed water, so double replacement acid-base.